Welcome to this presentation for Master of Data Science Research Project B. I'm Yuchen LIU. Today, I'll walk you through my progress on detecting satellite maneuvers by identifying anomalies in orbit data. This work is supervised by Dr. David Shorten. The presentation is structured into 5 parts: introduction, framework, exploratory analysis, evaluation results, and a summary. Let's start with the introduction. Satellites play a huge role in our everyday lives. They support communication, GPS navigation, weather forecasting, etc. In recent years, the number of satellites in orbit has grown rapidly, mainly because of large-scale commercial constellations like Starlink and Kuiper. This boom means that space is becoming increasingly crowded. As of now, there are over 10,000 active satellites orbiting Earth, which raises serious concerns about space traffic and the risk of collisions. What makes things more complex is that satellites don't stay in fixed paths. They often adjust their orbits deliberately, which is known as maneuvers, as shown in the animation. This happens for reasons like orbit correction, station keeping, or collision avoidance. Knowing when maneuver occur is important for maintaining safe and predictable operations and also supports broader needs like aviation safety and space policy planning. However, a key challenge is that satellite operators rarely publish detailed maneuver logs. To work around this, we use TLE data, which are public orbital element records that track a satellite's position over time. And maneuvers often cause sudden changes or anomalies in these elements. In the plot shown, you can see sharp jumps in brow remain motion for Fengyun 2H, which align quite well with known maneuver events. This leads to our core idea: detect anomalies to infer maneuvers even without explicit labels. Here's how we formally define the problem we're solving. The input is one time series at a time, each corresponding to one of the 6 orbital elements extracted from TLE data. An output is a binary label for each timestamp. 1 if the current moment is considered anomalous, meaning a maneuver likely occurred, and 0 if it's normal. As shown in the table here, we treat this like a classification task. For each time point, we use the orbital data to decide whether it's an anomaly. Now that we've covered the background and defined the problem, let's move on to the framework. Our approach uses a 2-step pipeline to detect maneuvers from orbital data. First, a time series model forecasts the next orbital value. This is the prediction step. Then, in the classification step, we compare predictions to actual values, compute residuals, and apply a threshold to flag anomalies. The predictor takes a window of recent orbital values, like the one shown in the illustration, and predicts the next point. By sliding this window forward through time, we generate a sequence of predictions across the full timeline. We implemented 3 different forecasting models to serve as predictors. ARIMA, a classical statistical model effective at capturing linear relationships and seasonality. XGBoost, a tree-based ensemble that handles complex nonlinear patterns. And LSTM, a recurrent neural network well suited for learning long-term dependencies in sequential data. Once we've generated predictions for the full series, we compute the residuals, the absolute differences between the predicted and actual values. To determine whether a residual indicates an anomaly, we apply one of 2 thresholding strategies. The first is naive thresholding, which uses a single global threshold across the entire series. If a residual exceeds this threshold, it's flagged as an anomaly. The second is local difference thresholding, which uses a dynamic threshold that adapts to recent local patterns in the data. We'll dive into the details of this shortly. In our setup, the classifier is quite simple. It takes the residuals as input and outputs binary labels, 1 for an anomaly and 0 for normal. This figure shows how naive thresholding works in practice. The blue horizontal line is our global threshold. Any points above the threshold, shown here in red, is flagged as an anomaly. Points below the line, shown in green, are treated as normal. One key limitation of naive thresholding is that it applies the same threshold across the entire time series without accounting for temporary shifts in the data. This becomes a problem when there's a local structure change, as seen around mid-2018 in this plot. In that segment, the residuals briefly follow a higher baseline compared to the rest of the series. If we continue using a constant threshold, many of these normal points during the shift, like the one circled, still fall above the threshold and get incorrectly flagged as anomalies. These false positives highlight why we need a more adaptive thresholding strategy that accounts for local context. To address this issue, we apply a simple transformation to the residuals. For each point, we subtract the average of a sliding window of its previous values. The equation shown in the middle is straightforward. The current residue minus the mean of the past residuals. This highlights how much a point deviates from recent local behavior rather than from a global threshold. As shown in the right-hand plot, this transformation helps eliminate many previous false positives. The core idea of this local diff thresholding is that a point should only be flagged if it significantly deviates from recent trends, making the classifier more robust to structural changes. Now that we've covered the full framework, let's move on to what we actually did with the data. We'll start with exploratory analysis. Although maneuver logs are typically not public, we obtained labeled data for 15 satellites. We examined all 6 orbital elements and found that Brouwer-Ming motion showed the clearest alignment with known maneuver events. As shown in the plot, only Brouwer-Ming motion exhibits consistent, sharp changes around the maneuver times, which are marked by vertical yellow lines, while other elements show gradual or unrelated variations. So we selected Brouwer-Ming motion as our primary feature and built univariate anomaly detection models around it. Out of the 15 satellites, we selected 5 to represent 3 difficulty levels. The easy ones, Fengyun 2F, 2H, and Sentinel-3A, show clear regular changes with stable patterns. Cryosat-2, our medium case, shows a dramatic shift in mid-2020, but still retains regular anomaly patterns. Saro, the hard case, has a structural shift at around mid-2016, and after that, there's also a reduction in anomaly frequency, as you can see from the plot. This range allows us to evaluate model performance across both clean and more complex real-world scenarios. Now let's take a look at the results. For each of the 3 forecasting models, we tuned their hyperparameters to get the best performance. The table here shows the optimal hyperparameters for each model on each satellite, but I won't spend too much time on the specifics. We'll focus instead on how well the models actually performed. Since we're using a 2-step approach, we first evaluate the predictor separately. We use mean squared error, usually referred to as MSE, to measure how well each model predicts the next orbital value. Lower MSE indicates better accuracy. Overall, XGBoost and LSTM achieve lower MSE than ARIMA, likely due to their ability to capture nonlinear patterns. The plot shows ARIMA's prediction for Fengyun 2H, which is in blue, aligning reasonably well with actual values, which is in black, indicating the model captures the trend. Then we move on to the classifier step. But to evaluate how well our anomaly predictions align with true maneuvers, we face a common challenge. Maneuver logs often don't align exactly with predicted anomalies. For example, in the left figure, the maneuver was recorded on October 20th of 2016, but the anomaly appears in the data on the 21st, nearly a full day later. To handle this, we use a method called event matching, which is commonly used in time series tasks. The idea is simple. If predicted anomalies fall within a tolerance window of a known maneuver, they count as true positives, as shown in the green circles. Here we use plus minus 3 days as the tolerance window. Anomalies that are too far from any maneuver are false positives, and maneuvers with no matching predictions are false negatives. Both are highlighted with red circles here. Using this event matching method, we can calculate precision and recall for any given threshold. Precision tells us what percentage of our predicted anomalies were actually correct. Recall tells us what percentage of true maneuvers we were able to detect. Since there's always a trade-off between those two, higher recall often means lower precision and vice versa. We don't just look at one threshold. Instead, we sweep through a range of thresholds from very strict to very lenient. For each threshold, we get a precision recall pair, and plotting all of them gives us the precision recall curve shown on the right. The curve helps us evaluate model performance across thresholds and choose one that best fits our goals, like minimizing false alarms or maximizing detection. For easy satellites, all three models generally perform well. We take Fengyun to F as an example. You can see that precision recall curves for all models follow a similar shape and enclose high area under the curve, which indicates effective anomaly detection. But when we move on to more difficult cases, the differences between models become more apparent. Taking Cryosat2 as an example, both XGBoost and LSTM achieve high precision across a broad range of recall, indicating more reliable anomaly detection. In contrast, ARIMA drops off much earlier, meaning it generates more false positives when trying to increase recall. Finally, let's take a look at the benefit of using local diff thresholding. On the left, we show a comparison between naive and local diff thresholding for an easy case, Fengyun to F with XGBoost. There's a little bit of improvement with local diff, but not much. But on the right with Saro, which is a hard case, you can clearly see a significant improvement in the precision recall curve when using the local diff approach. That's because satellites like Saro undergo structural shifts, and local diff thresholding adjusts dynamically to recent residual patterns. In short, local diff brings the biggest gains where we need it most, in the messier real-world cases where simple global rules don't hold up. While I haven't included every result, I've focused on the most important insights to give you guys a clear picture of our progress. To wrap up, let me briefly summarize what we've learned through this project. We designed a flexible and interpretable two-step framework that detects satellite maneuvers by first forecasting orbital values and then identifying anomalies based on residuals. Then we introduced precision recall visualization as a practical tool to guide threshold selection and evaluate the overall performance between different models. And critically, we applied a local difference transformation to residuals, which significantly improved detection performance on complex, non-stationary satellite orbits. Looking ahead, future work would include incorporating multiple orbital features to improve maneuver prediction and systematically evaluating the impact of the local diff approach across different model architectures. Here are the references cited throughout this presentation listed in the order they appear. And thank you for watching. I really appreciate your time and I welcome any questions or feedback. Feel free to reach out to me at the email shown on the slides. See you.